guys, we're now on video 11.2 and we're going to be talking about the main gas law that we're going to be using throughout the rest of this unit, and that's called the combined gas law. Before we jump into the actual law, I want to talk a little bit about pressure, volume, and temperature and how they're related to each other when we're talking specifically about gases. So let's look over here at the very first picture, pressure versus volume. A scientist by the name of Boyle, B-O-Y-L-E, came up with a law about how pressure and volume are related to each other when it comes to gases. And it's stated right here. It says when you decrease the volume, you increase two things. You increase collisions and you increase pressure. Collisions and pressure are kind of the same thing. Pressure just means, the amount of force of an object on something else. So let's look over here in this very first picture. This is our volume. Okay, this volume means space, right? So this is the space that these gas particles are taking up. And you can see that they're bouncing against the walls here. So you can see that these gas particles are exerting pressure, right? They're exerting a push against each other and against the walls of their container. But what happens when we take this volume and we cut it in half, okay? So we see here, volume is decreasing, okay, because we really cut it in half. What happens to the pressure when we do that? Well, all of a sudden, there's not as much space for these gas particles to move around in, so they begin to hit the walls more frequently, and they end up really just kind of moving faster. The less space you give them to run in, the more they're hitting the walls, which means the more push they're putting against the walls. So pressure gets increased when we increase volume. And that kind of makes sense. Like if I had a balloon and the balloon had like a fixed volume, but then I tried to shrink the balloon's volume, I tried to make that gas fit a smaller area. Why does our balloon resist us when we do that? Well, because the gas particles are exerting more pressure when you're trying to shrink the volume. Whereas if you're making the volume bigger, the gas particles have more room to flow in, and so they exert less pressure on the walls. So what Boyle kind of summarized this by saying you decrease volume, you increase pressure. And there's a term for this type of relationship where when one variable goes one way, the other variable goes the opposite way, and that's called inverse or indirect. And so we say that volume and pressure are inversely or indirectly proportional to each other, which just means, when one variable increases, then the other variable will do the opposite. Okay, the other variable will decrease. So we have one more relationship I want to talk about, and that is the relationship between volume and temperature, which is going to come into play when we're building our hot air balloon. So this law is really came up from this guy, this other scientist, Charles. So this is called Charles's law. And Charles basically stated that if you increase the temperature of a gas, then the gas will take up more space, okay? And so he says if you increase temperature, you're also the volume will do the same thing. It will also increase. So let's look at this first. It's called a piston. It's basically like an airtight container that we can change the space here. If right now we say the temperature is low, right? That's why I guess you can't see it. Can you see it's blue? I guess on your paper it's not blue, but on the screen it is. So the blue is indicating that these are cold particles, and so they don't take up a lot of space. They're not moving. They're moving really slowly, and so our volume is also low. But when we change our temperature, when we add heat, so here I'm adding heat. All of a sudden, when you add heat, what you're really doing is you're adding energy. And so these particles have more energy, and so they're moving around faster. So if you allow them to, they will take up more space. So temperature gets higher here, and then our volume, our space, also gets higher. The same could be said if we went the opposite direction. So if we have a balloon with really, really hot gas, and we put it in a freezer and we let it cool, what happens to all of those particles? Well, they're not moving as fast, right? So they take up a lot less space, so your balloon will shrink. So if you take a balloon and you put it outside in 90-degree weather, the balloon swells, it gets bigger. And then if you take that same balloon and you put it in the freezer, it shrinks. And that's due to Charles's law. So we say that these two properties, volume and temperature, they're directly proportional, meaning When one variable increases, the other variable does the same thing. The other variable also increases. Okay, so now that kind of takes us to our law, where we're going to be talking about our mathematical law. The combined gas law is written like this. It's P1 times V1 divided by T1 equals P2 times V2 divided by T2. So I want to walk you through each of these variables so that you know what they mean. So first, let's talk about the letters. P stands for pressure, okay? And pressure can be expressed in 3 different units. It can be expressed as ATMs, as millimeters of mercury, or kilopascals. And you can kind of see that on this part of the page, even though it's not shown in the video. It will be, by the way. I know it's not on your paper, but I'll scroll back so you can write it down. The T stands for temperature, okay, and temperature can be expressed as degrees Celsius, so that should be a degree there, or Kelvin. And the V obviously stands for volume. That's a bad V. It looks like a U, like ooloon or something. That's volume. Volume can be expressed in milliliters or liters. And now let's talk about the ones and the twos, okay? The 1 stands for the pressure, volume, and temperature before a change occurred in the gas. So think of this as being the initial conditions. It's the initial pressure, the initial volume, the initial temperature. The 2 stands for the pressure, volume, and temperature after a change occurred. This is also known as the final pressure, the final volume, or the final temperature. And so we're going to be given a problem, and we're going to have to look, we're going to have to identify the initial pressure, which would be P1, the initial volume, which would be V1, and the initial temperature, which would be T1. And then we also have to identify those same variables, but after the change occurred. And there's going to be one of these variables that we're not given. One of them that we're going to have to solve for. We're going to have to rearrange this equation to solve for. Okay, so let's back up here a second before we jump into the actual problem, and let's walk through some of the steps. So the first thing we do is we label all of our givens. So I kind of walk through the different things that you could label as. You can label something as P1 or P2. You can label something as V1 or V2, and so on and so forth. So let's label things first. It's important that whenever you see any of these units, ATMs, millimeters of mercury, or kilopascals, you label it as pressure. So let's do that first. Let's look at guided practice problem number 1. Guided practice problem number 1 says, a helium balloon with an internal pressure of 1 atm. So I'm going to stop right now. I'm going to box it. I'm going to put a P. I know this is pressure. I'm not going to identify which pressure it is yet, just because I want us to practice identifying pressure units first. And then we can go back and we can figure out whether it's the initial pressure or the final pressure. If I keep reading, I see here's another pressure unit. So I'm going to label that also as P because this is ATM. And now let's look at volume. Okay, so volume will either be in milliliters or liters. So if I read, I can see it says we have a volume of 4.5 liters. So I'm going to put a V here. And I keep reading, and I don't see another volume, but I do see it says here, what volume? So obviously, one of our volumes is going to be what we're solving for, because we're not given another volume. And lastly, we are going to find our temperatures. Temperature can be in degrees Celsius or can be in Kelvin. So if I'm reading through, I see here is a degree Celsius, so that is temperature. And then I see at the very end of the problem, there's another degree Celsius, so that's also temperature, okay? So now I'm going to go through and I'm going to add my 1s and 2s. And you're going to get pretty confident in doing this. So if you want to label the 1s at the very beginning when you're finding out if it's pressure, that's fine. It says a helium balloon with a pressure of 1 atm and a volume of 4.5 liters at 20 degrees Celsius is released. I try to find the action word or the change that occurs. The pressure, volume, and temperature that happens before that change are all your 1s. It's supposed to be 1. The pressure, volume, and temperature that occurs after the changes are your 2s. So this is going to be P1, V1, and T1 because they all occur before the gas is released. The gas being released is like the change that occurred. So this is going to be V2, this will be P2, and this will be T2 because they're all occurring after the change because it's asking what will the volume of the balloon be? What will it be? It's talking about future tense, so it's talking about after the change. Okay, so I've labeled all my givens. That's the first part. Now, the second step is to convert units. This is really, really important. It doesn't matter what pressure you're in. It could be ATMs, it could be millimeters of mercury, it could be kilopascals, but whatever the pressure unit is, it's got to be the same pressure. So if P1 is in ATMs, then P2 also has to be in ATMs. If one of them is not in the same unit, then you need to convert one of them to be the same unit. So for example, if this was in ATMs and then the P2 was in millimeters of mercury, we'd have to convert one of them. It wouldn't matter which one you convert to, they just have to be the same unit. So same pressures, and you also have to have the same volumes. So since we have liters here for volume, what does that mean? What unit will we have to have for our second volume? Well, it'll have to be liters because the units have to be the same. So we have same pressure, same volumes, and then all temperatures always have to be in Kelvin. It can never be in Celsius. If you see right here, both of our temperatures are in Celsius. So before I even move on, I got to convert those. So I'm going to cross this out because we're not going to use these Celsiuses anymore. We're going to have to use a conversion. So how do I convert 20 degrees Celsius to Kelvin? You should remember from our previous video that if you just add 273, then you can get Kelvin. So this is going to be 293 K. That is, this is T1. We just previously labeled it T1. This, negative 20, I would take negative 20. I'm still going to add 273 to it. Okay, and what do I get? 253 K, and that would be my T2. Okay. So now that we've labeled everything and we've converted any units, now we can plug our numbers in. So I'm going to scroll down here just a little bit. And our equation is up here, but I'm going to kind of rewrite it. It's P1 times V1 over T1 equals P2 times V2 over T2. So let's plug those numbers in. What's P1? P1 was 1 ATM, so I'm going to put 1 here. V1 was 4.5 liters. T1 was, remember we changed it, it's 293 K equals, and what's P2? P2 is 0.6 ATMs. Volume was what we were looking for, so I'm going to leave that there. We don't know that. T2 was, we converted it. It was negative 20. So now that I've done that, I want to solve for this guy. I want to solve for V2. So it's really an algebra problem. First thing you need to do is I want you to simplify your numbers, okay? So, for example, if you have the numbers up top here, we're going to just multiply them together. So 1 times 4.50 is 4.50. I'm just going to reduce all of this. I'm going to put this in the calculator. So I'm really doing 4.50. Let me do that right now, 4.50. And I'm going to divide it by that number, which is 293. So I have 4.50 divided by 293. And I get 0.015 equals, and I have 0.6 still, right, times V2 divided by 253. So I want V2 by itself. So that means I have to do two things. I need to get rid of the 0.6, and I also need to get rid of the 253. I can get rid of the 253 by just multiplying both sides by it. Now I'm going to do 253 times 0.015 because I want to simplify again, okay? And so here's what I get. I get 3.795 equals 0.6. So now let's get rid of that 0.6. We don't want that on that side. So I'm going to divide by 0.6. See how that's gone? See how that's canceled out? And so whatever you do to one side, you have to do to your other side. And so I'm taking that 3.795 and I'm dividing it by my 0.6. Okay, so the answer is 6.3225 equals V2. And so before we're done and we box our answer, we need to make sure we know what our units are, okay? So let's think back. One of the rules was same pressures and same volumes. We see that our units for pressure, do you see how they're the same? They're both ATM. So the same applies for our volume. The volume we were given was in liters, which means our answer also has to be in liters because you gotta have the same unit. So this is liters.